In 5.1, the last subject we're going to cover is showing that f and f inverses are actually inverses. So we need to check to make sure that they are inverses or look to see if they are not. There are several different ways to do this, but today we're just going to talk about the finding the inverse of one and comparing it to the other. So if we look at example number 7, we have f of x here. All I'm going to do is start using f of x, find the inverse of f of x, and compare it to the f inverse that we have right here and see if they're the same. If they are, then they're inverses. If they're not the same, they're not. But make sure you're very careful about, sometimes they try and trick you to where things look different, but they're really the same. So first step is to find the inverse, is to change f of x to y. So go ahead and do that. 2/5 x plus 1. Now, the second step is to flip your x and y. So remember, you're just changing x and y. You are not moving any numbers that go with it. Anywhere you see a y, you're going to put an x. Anywhere you see an x, you're going to put a y. Now we are going to solve for y. First step, subtract 1 both sides. X minus 1 equals 2/5 y. Now we have a 2/5 in front. We can either break this up into a multiply by 2 and then divide by 5 and do the inverse of that, or we can multiply both sides by the reciprocal of this fraction. So the reciprocal is the flip, so multiply both sides by 5/2. And remember, on the left side, you're going to have to distribute this 5/2. So you get this, y equals 5/2 times x minus 1. So looking at this right now, it does not look like this f inverse that we're trying to make it, but you need to be careful about that. If I do take that 5/2 and distribute it, this would give me y equals 5/2 x, and then 5/2 times -1 is minus 5/2. Now, another thing that you have to remember is that when you have two fractions and they both have the same denominator, you can combine them. So again, this still doesn't look like what we want, but if we combine them, this leaves me with 5x minus 5 on the top over a single 2. And that actually is the same thing. So f inverse of x is, again, 5x minus 5 all divided by 2. And that is true. So this tells me that these are inverses, right? They are inverses. Let's look at example number 8 now. So again, it doesn't matter which one you choose. You can start with this one or you can start with this one and work backwards. Either way, as long as when you find f and f inverse, they are the same thing. So I'm going to, first step, start with f of x, change it to y equals the cubed root of x plus 4. Flip your x's and y's. So this gives me x equals the cubed root of y plus 4. Again, don't move anything else except for interchanging x and y. I need to get rid of the cubed roots. If I start solving for y, get rid of the cubed root. So opposite of cube rooting something is cubing both sides. This gives me x cubed equals your cube root and your cube will cancel, leaving you just with y plus 4. So for y, subtract 4 both sides. Y equals x cubed minus 4. I went ahead and flipped both sides as well and replace that with f inverse. F inverse of x equals x cubed minus 4. And that is indeed what we have up here. If they did not match, if it said x cubed plus 4, they would not be the same and they wouldn't be inverses. But in this case, they are inverses. Now it's your turn. Try the last one. Again, find the inverse of f of x. See if it matches what they give you. If it does, they're inverses. If it doesn't, they're not inverses. So you've seen on the last example that these are not inverses. The last portion did not match up here, so they're not inverses. While wrapping up this 5.1, I wanted to talk about a couple of special properties of inverses. One of the special properties is that F and F inverse are symmetrical over the line y equals x. So if you graph a function and its inverse, it's really one of them is a reflection over the line y equals x. So I'm going to show you the example right here. So this is one of the examples we did earlier, x cubed plus 2 and the cubed root of x minus 2. We did find those inverses. So we know for sure they are inverses. We did this earlier in an example. So I'm going to go ahead and graph these, and I have the equation y equals x right here. So I'm going to go ahead and graph this. So you have the cube, the blue is my x cubed, the red is my cubed root, and notice that if you take this ordered pair and flip it over, it occurs right here. Take this ordered pair, flip it over the line y equals x, take this ordered pair, flip it over the line y equals x. These are symmetrical about the line y equals x. This is true for every inverse, and that's because you're just taking the ordered pairs and you're flipping the x's and y's. Exactly what we were doing earlier with the ordered pairs, except now we're using the whole set of ordered pairs for a function. That also tells me something about the domain and range of the inverses. The domain and range are flipped. So what's the domain in the original function will be the range in the inverse because they're opposite and your x's and y's flip. So an important factor is that your domain and range are flipped on inverses. So you know that, for example, if you have f of x, if your domain was x is greater than or equal to 0 and your range was all real numbers, then the domain and range of the inverse is going to flip because you flip your x's and y's. So what's your y's in your original function here will then become your x's, all real numbers. And what your x's are, which was your original x's, will then become your y's. In this case, it'll change to y is greater than or equal to 0. Those are some special properties about inverses that hold true all the time.